Good afternoon, everybody. Welcome and thank you for joining us for the 2020 and 2021 medal talks for the Canadian Association of Physicists. And so we will now move on to our final talk of the day. And I would like to invite Richard Epp to turn on his camera and his microphone. Richard is the 2021 CAP Medal recipient for excellence in teaching undergraduate physics, to recognize his accomplishments in teaching and commitment to physics outreach. He consistently receives high teaching evaluations from majors and non-majors alike, and students commended his Thinking Like a Physicist series that replaced informal interactions during the pandemic lockdown. So I would like to invite Richard to share his slides and give us his presentation. Welcome, Richard.
Thank you, Rob, and thank you for everyone who has come out, and thank you for those three wonderful talks before mine here. So largely my talk, it will be a thank you talk. So first off to the CAP for supporting research, but also teaching in its various forms across Canada, and and thank you for awarding me this medal. It's a huge honor for me, of course. But when I think about it, I just think over the last 20 years of my teaching, the first half of it roughly was at Perimeter Institute for Theoretical Physics, doing outreach, and the second half has been here at the University of Waterloo, Department of Physics and Astronomy. Over those 20 years, really, I feel that what's happened is I've just been extremely fortunate to have been, given huge opportunities and support and resources and creative freedom to do just what I love, which is to interact with students and to share with them, the power and the beauty and the simplicity of physics, to really help them understand physics at some kind of a deep level. And so, yeah, so there's along the way, there's a lot of colleagues and, thousands of wonderful students to thank. So the title of my talk is on inspiration and intuition and teaching. So I thought I'd explain that a little bit. Let me just clear this screen here for a second. Okay. Yeah, so on inspiration and intuition in teaching. So of course, what we want for our students is deep learning. So what does that mean? Well, to me, it means having concepts in physics need to make deep sense. They need to be strongly intuitive. Okay, but that's not an easy thing to achieve. So that requires, on the students' part, a lot of hard work. We don't sort of teach students, we just create a learning environment in which they do the hard work of learning. And to do that hard work, they need to be motivated, right? Self-motivation. And so they need some kind of an inspiration for that, to do that hard work. And so what does that mean? Well, inspiration in the context of physics, for me, means to genuinely understand how simple, beautiful, and powerful physics is. But now this is kind of a catch-22, because that genuine understanding requires, having it make deep sense and be strongly intuitive. So how do you get there? And so this is a nice diagram in principle, but how does it actually work? So what I thought I'd do is take a few minutes to give you a simple example of, and this is in the context of, quantum mechanics, when they learn quantum mechanics. And so, how would I talk about, probably, one of the really great initial successes of quantum mechanics, which was explaining how it is that atoms can exist in our universe. And so there's a really nice, there's a lot of great physics education research stuff out there, simulations and so on. So this is a great one by Falstad. And so this is a simulation of the quantum wave function of an electron in a hydrogen atom. Okay, so let me just rotate so we can see the XZ plane. Okay, and so the first thing is that, the classical intuition that students have of the electron in the atom is that it's like a planet orbiting around the sun. And so let's put in a state here. So let's say the first excited state, n equals 1, some angular momentum, and say m equals 1. And so we zoom in here, And this great little simulation, what it shows us is, the wave function of the electron, which is sort of like a donut-shaped, torus-shaped wave circulating around the nucleus of the atom. And so the classical intuition that the electron circulates around the atom is a good place to start. But of course, the trouble is that that a point particle orbiting like this around the atom is going to radiate, and the energy will be released, and the electron will spiral into the nucleus, and the atom will collapse. And so the classical model fails. And so how is it that the quantum behavior of the electron solves this problem? And so by quantum behavior, so so this is sort of something after the students have been in a quantum mechanics course, intro quantum mechanics course, say first year, for a couple of weeks, and we've talked about waves and superposition and complex waves and the wave in the box and so on, particle in a box, et cetera, et cetera. And so we've they've had some introduction. This is sort of like a capstone sort of a topic, which is how this quantum behavior, this electron behaving like a wave, can explain immediately the stability of the atom. And so we have an electron circulating around, so there's definitely some angular momentum, and that angular momentum in this case is coming out of the page. There's some physical angular momentum there, but that angular momentum is definite. And so the angular position by Heisenberg uncertainty is completely indefinite. And so it's like a free particle. And so it could be found with equal likelihood at any instant of time. It can be found with equal likelihood anywhere around that circular orbit. So it's uniformly distributed, the probability distribution. Okay, and so so what that means is because the electron can be in that superposition of multiple positions at the same time, it means that effectively the electron is functioning like a uniformly charged ring. And so if you spin a uniformly charged ring, you'll get a static electric field and you'll get a steady magnetic field, but there'll be nothing dynamic. So you won't have an electromagnetic waves, there will be no electromagnetic radiation, and bang, the fact that the electron can behave like a wave immediately solves the stability of the atom problem, and atoms can exist in our universe. Right, and so now in this setting here, the color indicates the phase of the wave function as you circulate counterclockwise around the nucleus, and we can turn that phase off. So effectively, the magnitude of the wave function, and so the probability would be the square of that, and you see that it is perfectly static. And so what we have is basically a stationary state, and quantum mechanics solves the stability of the atom problem. But then as soon as you have that, then you can show students some really interesting facts. So let's turn back on the phase. So we're seeing the full wave function here. And if an electron can orbit counterclockwise around the nucleus of the atom, well, then it can also orbit clockwise. And so here is the clockwise. Here's the electron orbiting clockwise around the nucleus of the atom. And then the beautiful thing about the electron being able to behave like a wave, it means that anything a wave can do, an electron can do. And so we can consider a superposition of the wave rotating clockwise and counterclockwise simultaneously. For a wave, this is no big deal. And when you do that, and I'll just do that right now, I'll turn on right now there's the clockwise wave, and I'll add to it the counterclockwise wave. And all of a sudden we see this. And so what we recognize immediately is, oh, well, these are just, the standard p orbitals that you see, first typically see in a chemistry class. And so, but then the insight that you gain from this is that state that you're seeing there describes a wave that's circulating both counterclockwise and clockwise simultaneously. It's like a particle in a box. The standing wave is a wave moving to the left and right simultaneously. And so this clockwise and counterclockwise wave, there's constructive interference at these two p lobes, and there's destructive interference everywhere else. But the fascinating thing is that standard sort of p orbital describes an electron that is simultaneously rotating clockwise and counterclockwise at the same time, which is a really beautiful thing. And if you consider just the probability distribution, so turn off just the magnitude of the wave function, you square that guy, and you see it's perfectly static. This is a stationary state. It's not going to radiate. In fact, all of the excited state of the hydrogen atom are energy eigenstates are stationary states, and they will not radiate. Okay, and so then you say, well, okay, great. Now we've overkilled the problem. Now the atom isn't going to be able to radiate. Okay, but so how is it going to get from that excited state down to the ground state? Well, what happens is not spontaneous emission. What happens is stimulated emission. So either you're in a laser and you have another photon of exactly the right frequency, appropriate frequency, or you are just in a vacuum and there are vacuum fluctuations of the electromagnetic field. And so there's virtual photons. In any case, there's another photon comes along of the appropriate frequency and it induces a, it stimulates a superposition of the excited and ground state. So so it puts the system in, right now it's in an excited state, and it puts it in a superposition of excited and ground state. And then something absolutely remarkable happens. So right now we have a stationary excited state, and now we're going to add to it the ground state. We'll put it in a superposition of excited and ground state. Okay, and so now what we see is the probability distribution is now fluctuating. It's dynamic, it's time dependent. And so it's effectively exactly the same as a charged particle oscillating back and forth. And what does that do? Well, it emits electromagnetic waves and it carries energy away. And it will do this for the amount of time required for a photon of the appropriate energy to be released. And so, you don't tell students that, the electron, magically, jumps from this excited state to this ground state and emits this photon. Well, how does that work? Well, right there, you have an immediate classical intuition in how these transitions work. And so the point is, what you're trying to do is you're trying to start students with their classical intuition, and you're trying to, bring them up to a deeper understanding of quantum mechanics that isn't just sort of this mysterious thing, but is deeply connected to their classical intuition. The only thing they need to accept here is that electrons can behave like waves. And so there's this amazing, quantum mechanics is this amazing unification of classical particle ideas and classical wave ideas, a seamless unification that is extremely powerful and allows you to understand in very simple terms the stability of the atom, how atoms radiate, and all that other kind of stuff. So that's sort of what I mean by giving students sort of a deeper intuitive understanding of physics. Okay, and then, and this can also be applied in special relativity and in general relativity and so on and so forth. So that's really a lot of stuff that I've done in over time. So like I said, about the first half of my career was spent at Perimeter Institute. That was just an absolutely glorious time. So here is a beautiful picture of Mike Lazaridis, just sort of an extremely amazing electrical engineer, research in motion. And, he recognized that, technology, new technologies, foundational new technologies come from, new fundamental understandings, deeper understandings of physics, unifications, electricity and magnetism, electromagnetism, wireless technologies, et cetera, et cetera. And here is Howard Burton. So extremely intelligent, highly capable guy, freshly minted PhD from the University of Waterloo. And, the two of them cross paths and sparks fly, and out comes Perimeter Institute. And so the beautiful thing about Perimeter Institute, the vision here is that, sure, it's going to be a powerhouse research institution, but it's also going to have a very strong physics outreach into the community to excite, the general public about physics and what it's all about. And the amazing thing is, I was extremely fortunate to be given, the opportunity and the resources, and like I said, the creative freedom to be able to spearhead the development of the outreach program from scratch. And so I really thank Mike and Howard, because, those years that I spent at Perimeter doing exactly that, strongly shaped me as the educator that I am now of physics students at the undergraduate level here at Waterloo. I also want to thank the initial researchers, so Lee Smolin and Rob Myers. So these guys left tenured positions to come to this little clock tower building in the center of Waterloo and start this weird thing, whatever, Perimeter Institute, right? And so without that courage to come, and then there are very high stature researchers drawing other researchers in to make the whole thing grow, none of that would have been possible. So this is of course the first Perimeter Institute building, and I remember because there was this Howard at the very beginning. There was this Howard, Colleen Brickman, and an administrative, highly excellent administrative person, and myself. And we just walked into this building here in Waterloo and thought, is this a good place to start Perimeter Institute? And of course it was, because it started out as this bar, and so there were pool tables, and so we kept the pool tables, and Lee Smolin and Rob Myers came, and the whole outreach thing started, etc. It's called Times Square, and so when the physicists moved in, we called it Space Times Square and made a neon sign. So anyway, so the outreach at Perimeter Institute. So, I needed to get to know, what excites students, and how is it I can get, obviously black holes and quantum teleportation and all that stuff, but how can I explain that stuff to them in a way that's going to make enough sense that they're genuinely think physics is cool, right? It's not just sort of sensationalization. Anyway, so I got in my car and drove all around Southwestern Ontario, visiting hundreds of classrooms, and talking to teachers and the students, and these quickly grew in popularity and size. Like, I remember going to a small town, and the entire school, grades 7 to 12, would be in the gymnasium, and I'd be like up there doing physics demos and getting them excited about physics, and lots of questions afterwards. Anyway, so eventually, in the long run, this just spread nationwide. And so there were Physica Fantastica presentations, sort of inspirational presentations for large groups of general public and students at the Canada-wide Science Fair and so on. And then Go Physics. These were like national trips to schools, workshops, hands-on workshops and demos. I remember, hauling my electron diffraction apparatus through, countless airport scanners and stuff like that. Anyways, it was great. And then right early on, I started Young Physicists for Canada, which quickly became international, became the International Summer School for Young Physicists. And this was a fantastic opportunity for 40 select students from around the world, half Canadian, half international, half female, half male. And they come for like 2 weeks of super intense, all things theoretical physics at PI. And so the first week was lectures I put together on special relativity, general relativity, and quantum mechanics, and other cool things that researchers were working on at PI. And then the second week was, the researchers stepped up and they gave talks to the students, and they also met with the students in small groups to do sort of like mock research projects. And so it was just a fantastic opportunity for these students, which, many of them, it just catapulted them into a career in physics. Just a huge opportunity for those students. So there's many people to thank. I mean, so two, huge supporters and mentors, besides, Howard. So I was at Perimeter for a while, and then I went to Waterloo, and then I came back. And then John Matlock was in charge of the outreach, and then a little bit later on, Greg Dick. And so these are two really strong mentors and supporters that I'd like to thank. And one of the fun things I did with John Matlock was these Alice and Bob in Wonderland animations. So I'll show you just a quick example here, just 1 minute.
Hey, Bob, I've been wondering what keeps us stuck to the Earth. Why don't we just float out into space?
Or some gravity.
But how does it work? All I really know is that this feeling of being pulled down is just like being pulled back into my seat when a car speeds up.
You're saying gravity isn't a force pulling you down, but instead the ground is accelerating up? Like a car seat accelerating forward?
Why not? If I fall off a ladder, I feel nothing, like an astronaut floating in space. It seems to me it's the ground that's accelerating up, not me accelerating down.
But then wouldn't the Earth have to be expanding faster and faster?
I need to think deeper, like Einstein. Maybe his warped space-time can make sense of this. That's a powerful idea.
And then after that, there's some, demo of everything you want to know about Einstein on a beach ball and all kinds of stuff like that. So anyways, I just really want to thank that, as time went on, there were more people who entered the outreach, or the outreach team was ever growing. And so there's lots of people to work with eventually. So Marie Strickland and Damien Pope and others, great people to work with. And of course, over the years, many, many teachers, too many to mention, except I'll just mention two is very special to me, Dave Fish and Dave Vrolik, who I really learned a lot from. This is Fish playing with balloons here. I also really wanted to thank the researchers. So here is, for instance, for stepping up at, International Summer School, giving talks, and especially working with the students in small groups. So this is, for instance, Fotini Markopoulou in one of the first summer schools, working with a group of students, and just thousands and thousands of students. So all of my work there was has motivated a lot of students to pursue physics in undergraduate studies, and it's been a real pleasure working with them. And then sort of halfway through or whatever, I eventually ended up at Waterloo, Department of Physics and Astronomy, which is just really rich with teaching and learning opportunities. So again, I was given the opportunities and resources and creative freedom to do what I love to do. So I was given carte blanche to develop 3 courses. So one is general relativity for second-year students. So of course we have a 4th year general relativity course, which is a wonderful course, but it's pretty math intensive and not all of our students take it. And that's a shame because you can't graduate with a physics degree without understanding a little bit substantial about what Einstein said. And so anyway, so I made a course like that for 2nd year students, which was sort of light on math and heavy on just physics concepts and geometry and stuff. And they just loved that. There was an intro astro course, which was the first course in our sequence of courses for the then new physics and astronomy program. And that was just basically, let's talk about some cool things in astrophysics, like, white dwarfs and neutron stars and black holes and dark matter, dark energy. And let's try to understand those things using very, very simple ideas in classical physics and in modern physics, just to show them the power that even simple physics ideas have. And then another course, Big Ideas course, which was sort of a life, the universe, and everything course, in which I was able to, focus on, the power of physics to help answer some of our deepest questions. So in terms of origin of life, or nature and origin of the universe, or in terms of theories of everything. So there's a discussion on the holographic principle in that course. Just a lot of fun. The students love that course. This is general science, 2nd year general science students. And then outreach. I also was given the opportunity to do some outreach. I still love doing outreach. So together with Heather Anderson, who is here, she's our sort of lab and demo equipment guru. So she, did the equipment side. I did the worksheets for students to work on and so on. So that now reaches, about 1,000 students a year, high school students a year in non-COVID times. So thank you, Heather. And the main thing I work on is this large enrollment mechanics course, which I'll say a few words about in a minute. But I just wanted to, just say thank you to several really key people that have played a big role in making all of this possible. So those are, really strong mentors and supporters. So there's Rob Mann here, who is no stranger to the CAP. And in fact, he won this same, or was awarded the same teaching medal that I've just received. So it's quite an honor to follow in Rob's footsteps. And, I've known Rob since my graduate school days. And, at my time here at Waterloo, he's made available opportunities for me to work with students on the kind of research that I work on, which has been really, really great for me and the students. And I must mention Rohan Jayasundara. So Rohan is, so we overlapped like this. So he's been here forever. And then we overlapped for a couple of years and then he retired. And so Rohan is, was an extremely well-loved lecturer. He's the kind of guy that could, get those engineering students out on a Saturday morning tutorial with nearly 100% attendance without any, bonus marks or anything like that. They just loved him, and he was a fantastic advisor. Did the bulk of the advising. He knew every student. And so, I sort of, when he retired, the idea was I sort of roughly try to fill his shoes, which of course I can't do. But anyways, as doing, teaching, lecturing and advising students. So, I really thank Rohan, as Rohan would say, I taught him everything he knows. And he taught me a lot. And in terms of like running a great department, this is a great department. Waterloo is a great department, and it's not easy. That doesn't happen by accident. It takes, it's hard to do. And so I just wanted to mention Jeff Chen here, who was the chair when I was hired. So thank you, Jeff, for having, faith in me that I could, be a useful member of the department. And there's Brian McNamara and Michael Ballo, current chair and the associate chair for a long time. He just stepped down. And so these two of my colleagues have made it a really great department to work in, and they've been really supportive of my own work here. So thank you. And wonderful teaching colleagues. So some who with whom I have co-taught courses, and others not, from whom I've learned a lot. Rob Hill and so on. And great students at Waterloo. Waterloo is a fantastic place, and it attracts well, a wide range of students, but there are a lot of students at the high end as well that are just great students to work with. They're all great students to work with, but it's really been a pleasure to work with the students here. And so my last slide here is I wanted to focus on this, the bread and butter main course that I do, which is the first year mechanics course for our physics majors. It's a large enrollment course. I've been teaching that, for many years. And and then in 2019, fall of 2019, we had Karen Cummings join the department. And Karen is an expert in physics education research. She's been involved in that community, that research community, since basically the beginning. And so it was really fantastic that Karen and I joined forces and were able to team teach this Phys 121 for 19, 20, and 21 now. And so, of course, 20 was the first full COVID term, and so really we sat down and thought, well, man, that's going to be hard on students just coming out of sort of a partly COVID high school, and then we wanted to make a course that would give them the best possible sort of experience, university experience, that they could have given the COVID circumstances. So basically, the course revolved around remote collaborative group work. It was focused on group work. And the reason for this, there's several reasons. One obvious reason is physics education research, says clearly that, done properly, group work is great for student learning. So check that box. But then also, obviously, it would allow students to interact with each other and meet each other. And so we deliberately had the groups cycle through a couple times, shuffle through a couple times, so that each student got to meet a bunch of other students in the class. And so they got a real sense of community. Yeah, I'm a physics major at Waterloo, I'm a 1A physics major at Waterloo, right? And I know people in my cohort, right? So community building, all that kind of stuff. And then, of course, it also had the very important and profound effect of supporting mental health. And that came clearly through in the student feedback at the end of the course. Strong message. And certainly compared to some of my other courses and stuff, man, this 121 course was really great at supporting my mental health, introducing me to friends and all that other kind of stuff. So, anyways, group work. So there were actually, the course, let me tell you what they did in the groups just very quickly. I don't want to take too much time. So the course is broken into 6 2-week segments, or modules, kinematics, dynamics, that kind of stuff. And then so in the first week, they will have 2 tutorials on Tuesday and Thursday. So the first thing that they hit is a conceptual tutorial, and that is, these were prepared by the University of Washington, and Karen was familiar with them. They're super, super high quality conceptual tutorials, and they deal with common misconceptions and so on. Because if you don't have the basic concepts, there's no point in doing anything else. And then on the Thursday, they get together in groups and they've worked through some sort of exercise problems, and they bring to the group, what they've done, what questions they have, and so on. And we had very structured group activities and so on. And then the following week, on the Tuesday, they have advanced problem, long answer problems, where we encourage them to, use as many of the tools in their physics problem solving toolbox as possible. Create good solutions. Draw a great diagram, a meaningful diagram. Start with general equations, specialize at the end. What happens when you set L equal to 0? What do you think intuitively? Does that agree with what the math says? That kind of stuff. And then the last is the Thursday. That's sort of the culminating, or the fourth group activity is rocket science activities. So I developed these things. They're basically starting the year before and finishing, I guess, in 2020. So basically, we have a wide range of students here at Waterloo, from not very well prepared to extremely well prepared. And so we wanted something for really extremely well prepared students, and this gives them a really interesting real world context in which to apply the Physics 121 concepts. Anyway, so that was the group work. And coming into that group work, before they started that module, I put all of the lectures onto Lightboard lectures, which was a lot of fun, a lot of work, but a lot of fun, and the students really liked that. And as Rob said at the beginning, there were Thinking Like a Physicist sessions on Sundays and so on. So anyways, the course, I think, was a real success in terms of the things that we wanted to achieve to help the students through that difficult COVID term. So yeah, I guess I'll wrap up there. I think I've used up my time. So thank you.